Okay, so we're back. This is part 2 of lecture 13. So we are going to talk about, in this part, we're going to talk about Cantor's proof of the power set theorem, or Cantor's theorem rather. Okay, so before we get there, first let's talk about power sets. What are they? So a definition to begin with. So let A be a set. Be a set. So that's a definition. Then the collection of all possible subsets of all possible subsets of A is another set and is called the power set. The power set of A. Notation depending on the book that you read usually is script P that indicates the power set of set A. Alright, so let me just do a small numerical example. So let's say we have the set A, and the set A is made of 4 elements. Actually, let's say 3 elements, so it's easier. So the set is made of A, B, C. Yeah. Okay. So what are some of the possible subcollections or subsets of the set A? Well, for one, this is a subset. The subset containing only the element A. Then there is the subset containing only element B, the subset containing only the element C. Then a possible subset is subset containing only A and B, the subset containing only A and C, the subset containing B and C. So 1, 2, 3, 4, 5, 6. Do I have any others? So I have AB, I have AC, I have BC, I have what else I have? I have the entire set ABC. Am I missing anything? I'm missing the empty set. This is notation for the empty set. Make sure not to write the empty set as, so empty set is not the same as this. It's a mistake. This means you have a set with one element in it, namely this symbol. But when you just write this, you mean the empty set, the set with nothing in it. So let's see how many elements I have. 4, 5, 6, 7, 8. I think I'm missing one, and what could be that one element that I'm missing? I have A, I have B, I have C, I have AB, I have AC, I have BC. I have the set ABC. Okay. I don't think I'm missing anything. Anyway, so these are the possible subsets of A. But the set of all possible subsets of A is itself a set, as I'm saying in the definition. So it's another set. What are the elements in this new set? the elements in this new set are subsets of the original set. Okay, so when the case is finite, meaning when you have a set with finitely many elements, if your set has n elements, then your power set has typically 2 to the n elements. So in the finite case, so if set A has n elements, then I'm going to say in general, if set A has n elements, then the power set has 2 to the n elements. Okay, so obviously if A has n elements, power set of A is strictly larger. Since 2 to the n is surely larger than n. So the finite case is not really so interesting. What we are interested in is the infinite case. When you have finitely many things and you take all possible subcollection, the set of all possible subcollections of this finite set, then you have 2 to the n of those, and obviously is larger. But if the set is infinite, then what do we mean by the power set of an infinite set? How many possible subcollections you could have of an infinite set? Well, infinitely many. So the question is, how do these infinities compare? Meaning the infinity of an infinite set and the infinity of its power set. Is it always true that the power set, even in the infinite case, is strictly larger than the cardinality of the set itself? The answer is yes, and that is actually the so-called Cantor's theorem. Cantor's theorem. Okay, it states the following. If A is a set, finite or infinite, then the power set of that set is always strictly larger than A. Cardinality wise, that's what we mean. Again, depending on the book that you read, sometimes the cardinality of a set is denoted in the absolute value notation, and sometimes with a bar. It makes really no difference. So notation wise, we want to show that the cardinality of the power set of a set is always larger than the cardinality of the set A. Here, the absolute value notation means, it doesn't mean absolute value, it means size of the set or cardinality of the set. Okay, so here we are going to more or less follow the same line of thinking as we did with the reals being uncountable. And we are only going to discuss the infinite case because the finite case is rather obvious. So, proof. Case when A is infinite. So if A is infinite, then power set cannot possibly be finite, so power set is also infinite. And then we want to not combine, but compare these two cardinalities. And to do so, we need to establish a one-to-one correspondence. If such one-to-one correspondence exists between these elements of these two infinities, then these two infinities are of the same size or the same cardinality. Otherwise, if we can't establish that one-to-one correspondence, they are not. So again, let's say that such pairing is possible, meaning it is possible to establish a one-to-one correspondence. And I'm going to write a list, and I claim that again the list is complete in the sense that every element of the set A is paired up with some power set of the set A, and every power set of the set A is paired up with some element of A, and there are no pairs, there are things that are left, there are no things that are left unpaired. Okay, so for simplicity, let's say that the set A is made of, I don't know, letters and numbers, infinitely many. A, B, C, D, 1, 5, 7, question mark, star, and so on. Let's say you have an infinite set and you have letters and symbols and numbers in it. Infinitely many of those. Okay, so what I'm going to do, so let's say that a one-to-one correspondence is possible. Okay, with other words, we have the following list. Here I'm listing things from the set A, and here I'm listing things or elements from its power set. Okay, remember, the elements of the power set are subsets of the original set. These are the new elements of the power set. Alright, so let's say I have things listed here: A, B, C, D, 1, 5, 7, question mark, star, and so on. Okay, and let's say that the set A is paired up with some particular subset of the set A, meaning some particular element of the power set. And let's say this particular subset. Okay, keep in mind C and F are there, or all letters of the alphabet are there. Okay, so, and let's say that B is paired up with A, B, question mark, and 5. Okay, let's say that C is paired up with the empty set. That's another notation for empty set. Okay, and then let's say that D is paired up with the entire set itself. Let's say that 1 is paired up with 1 and 5. Let's say that 5 is paired up with K, L, G, D. Let's say that 7 is paired with some subset of A, or some element of power set of A. And this goes on. So question is, is this in fact complete? Could such thing is possible? Could you may actually have a one-to-one correspondence? To show that we can't, we can create, or we're going to come up with a particular element of the power set that for sure is not going to show here. So if you claim that your list is complete, it means that whatever possible subset of the set A that you can think of definitely is listed here. But if you can come up with one that for sure is not here, then your list cannot possibly be complete. And that should work with absolutely any arbitrary list that, or any arbitrary pairing that you create. So I'm moving here. So we want to create a particular element of power set. So let me call it M for missing. This is an element of the power set, some particular subset of A, M for missing. And okay, well, what does this particular subset of A looks like? Meaning, what are its elements? Okay, could this be an infinite subset? Sure, absolutely, it can be. But anyway, so how do we come up with this particular subset? Here's the rule. So you're going to fill in the question mark, meaning for each element of A listed here in this particular subset, as follows. So the question mark will be decided as follows. If the let me just write the rule. If the element of A is in the subset it is associated with, then that element of A rather will not be in M. Otherwise it will be in M. Okay, what does that mean? So to decide on the first question mark here, you are going to look at the first pairing of this list. If A happens to be here in this particular subset, then A will not be the first question mark. But if A is not in this particular subset, then A will be the first question mark. So is A here? No, therefore A should be here. Okay? To decide on the second, we'll do the same thing. Moving on, is B in this particular subset? Yes, it is. So we skip this and then we move on. Is C in this subset? No, because that's the empty set. So C should be here. Is D in the entire set A? The answer is yes, because this is the entire set A. By the way, every set has as a subset of itself, is a subset of itself, and also has as a subset the empty set. That is true for any set. So is D in the set A? Sure, so we move on. Is 1 in this set? Yes, it is, so we move on, we don't put it here. Is 5 here? 5 is not, so I'm going to put 5 here. And then I'll keep doing this. Okay, so what guarantees that M actually is not going to show up here, or M is more than you can pair up, meaning M is not showing in this one-to-one correspondence that I'm claiming it exists. Why? Because M is unlike this. How so? Because if nothing else, A is in here and I'm making sure that A is not here. So if nothing else, these two subsets will differ by an element. A is here, A is not. Well, this subset will differ from this subset because B is here and I'm making sure that B is not here. Okay? By the way, elements in the subsets or in elements of A in the subsets of A are listed only once. So the same element cannot show well, no, that's not true. That's not true. I'll take it back. So, okay, moving on. Is it like the empty set? No, because if nothing else, C is here and C is not here. Is it unlike, is it like the set A? Well, no, because I'm making sure that D is not here. I'm making sure that this set and this set are different because 1 is here and I'm making sure that 1 is not here, and so on, and so on. So no matter what, if I'm creating this particular subset this way, I'm making sure that this subset A definitely is missing from this list here. So at the end, I don't really have a one-to-one correspondence. So let me just finalize this. So by using this criterion, we know that the M, which is an element of the power set, cannot equal, which is what I was saying a minute ago, cannot equal the subset corresponding to any element of A. Therefore, there cannot be no one-to-one correspondence. So this pairing cannot be. A one-to-one correspondence. And that will be true for any other arbitrary pairing that you may try. And this is true. Or any other pairing between A and its subsets or elements of the power set. So there are more things than you can pair up with elements from A in the power set. That means that the power set is larger. So the infinity of the power set is actually larger. All right, well, now the following questions may arise. We saw from last time and this time that obviously there are infinities that are of the same size and there are infinities that are of different sizes. For example, we showed that the infinity of natural numbers is the same as the infinity of the integers is the same as the infinity size-wise of rational numbers. And we showed that so size-wise, whenever we talk about these sets, we don't distinguish. Again, I repeat, size-wise. Otherwise, these are very, very different sets. I'm not talking about the nature of elements in these sets. I'm talking about their sizes. So size-wise, I'm talking about the same set here. We just showed that last time that these infinities are not countable, and the infinity are countable, and the infinity of reals is uncountable, meaning the infinity of reals is larger than this. So they are smaller than the size of the real numbers, the infinity of real numbers. So the first question is there an infinity that is surely larger than n, but smaller than the infinity of reals? Meaning, between those two different sizes of infinities that we discovered, is there some other infinity in the middle? It's not too bad or not difficult to prove that the infinity of the power set of counting numbers actually is the same as the infinity of real numbers, but we're not going to go over that proof. So the question really is there an infinity between the counting numbers, meaning larger than that, but less than the infinity of its power set? I'm going to answer that question, but I'll get back to it in a minute, as it has a strange answer. So what else can you ask? Is there an infinity larger than r? Is there an infinity larger than r? Well, the answer is yes. What would be an infinity that is larger than r? Its power set. Power set of reals will be larger than reals by what we just proved. So the answer is yes, and that is the infinity that is larger than the infinity of r. So question number 3, are there infinitely many different sizes of infinity? Are there many different sizes? Sizes of infinities? I'm not going to write the answer, but I'm going to say what the answer is. The answer is yes. Would there be an infinity larger than, for example, the infinity of power set of r? Yes, the power set of that. So the power set of reals is one infinity, but the power set of that is an infinity larger yet. You can keep taking the power set of a power set of a power set of a set infinitely many times, and each time you take the power set, you come up with yet a bigger infinity, again according to this theorem. So the answer is yes. 4, is there a largest infinity? Is there a largest infinity? Meaning, well, the answer would be no, because if you think that there is a largest infinity, then what about its power set? Its power set, if there is a largest, then its power set will be larger than that. So the answer is no. So in some sense, this is the same as asking, is there a set of all sets? Is that such universal set that contains all other sets that you can think of? Well, for truly enormous quantities like this, the concept of a set as just a bunch of things is not appropriate. And in that context, the definition of a set is something else. It's not just a bunch of things, but it's a much more intricate definition, and the set theory is a branch of mathematics that deals with that. Now, getting back to this first question. This first question can be answered yes or no. So why is that true? So the first question otherwise is known as the continuum. Hypothesis. Okay, how can it be yes and no? In 1940, I believe, Gödel proved that it's impossible to disprove this. He proved that it's impossible to disprove, and I think in the 1960s, Paul Cohen, he died a couple of years back, and I think he was at Stanford, and I also think that he was a professor at Brooklyn College, by the way. Cohen proved, so Gödel proved that it's impossible to disprove, excuse me, and Cohen proved that it is impossible to prove. It's impossible to prove it, it's impossible to disprove it. Two different people proved those statements. That's why this remains as a hypothesis. I mean, it's known otherwise as, it's not a hypothesis, but it's known as a continuum hypothesis. It does certainly have a bizarre answer, but that's the answer. A very, very interesting subject, but this will mark actually the end of this lecture, and until next time.